Welcome everyone to our first workshop of the winter term. Incredibly excited for the term ahead, but today's topic will be input management in video game. My name is Young. I'll be representing the Gamers Union to bring you this topic. So the goal of this workshop is to give you a brief history and evolution of how input works in video games and a little bit about how input affect the actual design and development of a video game, as well as we'll talk about some input devices that are less commonly known to us, and we'll also get a little bit practical and see how to implement a scalable input system in Unity. So first of all, a little bit of a history lesson here. I promise you won't be boring. Uh, so let's start with the very beginning, which are arcade games. So each arcade cabinet, arcade machines, they all came with only one game on each arcade. And this is great because the designer of the game can design some specialized input devices like buttons, sliders, joysticks that are only needed for that one game. So you can see on the two arcade machines here, Pong, they needed two sliders to control two players on the left and the right, and Street Fighter 2. They need a set of joysticks and buttons to control the two fighters. But when video game console hit the home market, they can't design specialized input for every game anymore. So we need something universal, and Nintendo set the standard with the NES controller, and is a very simple but effective controller. So Super Mario Brothers was one of the first game on the NES, and it used this. It utilized this controller very well. But as gaming evolved, we started asking the question like, what if the input to a game can be more than just binary value, right? The NES controller, they are buttons, and when we press them is true, when we let go of them is false, right? We have only two states. But can we read like an analog input? Can we read it to can the input value be a range of value instead of a binary? So the Nintendo 64 controller famously introduced an analog stick. So, and Super Mario 64 is, I think, the best game that sort of showcase how this analog stick is used. Mario is able to run around 360 degrees, very, very natural. So that's the analog stick, and this is one of the most important sort of innovation in game controllers, because every major game controllers moving forward has featured an analog stick in one way or another. And in fact, the Xbox controller has two of them, and this is very important because it basically set the blueprint for like how most AAA games are controlled in the modern day. The left analog stick for controlling the character, and the right analog stick for controlling the camera. So yeah, it was very influential. And recently, there is a new trend towards VR game, where they sort of break the confinements of what a game controller should and can be, and introduce a whole new way to play. Movement tracking and a VR headset. So that's where we have been and where we are now with video game controllers. But what about the PC? It's also a big platform that a lot of people play video games on. So obviously, the mouse and the keyboard were not designed to play video games. It's a privilege that game controllers have. They were designed specifically to play video games, but not the mouse and keyboard. So the early days of PC games usually use the mouse and keyboard setup in a very conventional way of how people usually use their computer. Clicking on stuff, using arrow keys, etc. So we usually see text-based or point-and-click adventure games that make very simple use of this of the mouse and the keyboard. But the WASD standard that we are familiar with today was popularized when first-person shooter games sort of exploded in popularity in the late 90s and the early 2000s for PC games. But when it first hit the scene, when first-person shooter games first hit the scene, the key mapping was actually all over the place. Some game uses the mouse and the keyboard. Some games only use mouse. And this standard was only popularized from 1997 when a professional Quake player won a tournament using this setup. And so this marks sort of the beginning of the WASD standard. And over time, this standard was adopted for most games where you can control the camera, not just for first-person shooter games. And so this is something that we sort of expect with every big budget games nowadays. WASD for controlling the character and the mouse for controlling the camera. So that's where we are now with the PC platform. So you might have noticed the WASD setup leads to most of the keys that we use in our game are sort of located on this side of the keyboard, right? Usually shift for run, control for crouch, R for reload, the number row for selecting weapons. So this convention was designed because these keys are easily accessible for players who are using this setup. So that's how we got here, and that's how the modern standard was set. And also recently there is, well, not recently, it's something that's has happened in the past, but it's becoming increasingly popular, is allowing the player to remap the input of their game. So you can map the action to a dedicated input that you want, not what the developer decided it should be. So this greatly improved accessibility. And let's look at some games that does some interesting things with their input for better or for worse. So Resident Evil 4 on the PC, it actually used the arrow keys for aiming instead of the mouse. Now granted, if you play Resident Evil 4 Steam version like right now, this problem I think is fixed, but the original PC released was used this input system. And the general consensus was that people did not like this at all. They said it's wonky and is a frustrating experience because they have come to expect that aiming should be done with the mouse. So, lessons learned: a bad sort of input mapping can ruin what is an otherwise great experience, right? Resident Evil 4, I really like it. And players like the standards that they are already familiar with and they expect it, and well, they won't be happy if this standard is broken. And second case study that I'd like to talk about is also a very interesting game. So this is Ego or Igo, not sure how to pronounce it, but it's basically a game where you have an in-game companion, and you have to sort of protect this in-game companion of yours. And there is a button on the controller, a dedicated button that is mapped to the action of holding the hand of your companion. And if you let go of this button, your character will actually let go of the hand. So if like you're crossing a dangerous bridge and you let go of this button, your companion may fall down that bridge. So this is a great example of how input can actually influence a design of a game, because this is absolutely intentional, and it sort of conveys how the main character of the game feel to the player who is playing the game. So it's a really, really good example. And what about online games, right? We talk about like how input is handled in the modern day, but online games are very popular in the modern day as well. So how does input work in a multiplayer game, an online multiplayer game at that? So there are several sort of architectures and several way of handling handling an online game: peer-to-peer networking, client-server networking, and local multiplayer. So local multiplayer is very straightforward. We have one device and we have several input devices, and the input is handled only locally. So a peer-to-peer architecture is when many computers share their resources and communicate in a decentralized system. And this is somewhat uncommon in how online games work, because it is quite difficult to connect over many clients, and it is also rather difficult to prevent cheating in these online games. The client server architecture is more common for online games because the server is designed as a centralized system that sort of handles every client. And this is a lot better for online games because we can prevent cheating and do a lot more stuff this way. And of course, we talked about local multiplayer. It's very straightforward. We just have one device and multiple input devices. So let's have a look at a way to transfer data across clients. So obviously it's actually the biggest issue when we talk about online games is lag. So there are two sort of challenges that arise from this lag. So challenge number one is if the local client is updated whenever the true state is received, and network congestion will lead to poor user experience. And challenge number 2 is if the network delay for one or more clients is relatively significant. Events from client that are generated from old global states and are applied onto the current true global state. This can lead to a frustrating behavior on the client's end. So this may sound very wordy and technical, but we're going to break it down and see how it works. So challenge number 1. Let's see. So we're going to look at how the source engine, which is the game engine behind games like Team Fortress 2 and Counter-Strike, how they introduce a solution to these challenges. And let's see how it works. So the source, the server of this engine, sends 20 updates per second. So a quick reminder of the actual challenge is that if the local client is updated whenever the true state is received, any network congestion will lead to poor user experience. So what this means is that whenever, say, you place your crosshair on an enemy and it turns red, if your network is, if your latency is high, the game itself, the server, might not detect that your crosshair is red, and you must be able to hit the enemy if you start shooting. So how is this problem solved by source? Is that the source server send 20 updates per second. Basically, it update the states of your aim 20 times per second. But if rendering is only based on these updates, it would lead to a slow and choppy game. And so interpolation is used on the client side to fill in these gaps between the 20 times per second. And if the user presses an input and sends the event to the server, so when you fire your weapon, the game client updates the game state accordingly in anticipation of the input result. And the client uses the local update until the server sends the true value. So that's how the source engine sort of solved challenge number 1 that we introduced when taking things online. But what about challenge number 2? If the network delay for one or more clients is significant, events from clients are generated from old global states and are applied onto the current true global state. So if you're playing online with your friends and they have a lot more lag, or not lag, but like latency, network latency than you do, or you have a lot more network latency than they do, then this can lead to a frustrating behavior on the client's end, on our end. So how is this problem solved in the source engine? So the server gives a history of all player positions in the last second. And when a user command is executed, such as firing of a weapon, the server estimates the time when the packet was created. So a packet is basically information that you send to the server to have them process. And and the server move all players back to the position at the time that the packet was created, and calculates any events that occurred as they at the same state, and resets the position to the latest state and triggers the event. And so this is an animation that sort of depicts a hit registration issue in Team Fortress 2, which is hilarious. So I'm gonna let it play out because I think it's really cool. So you can see that some of the hits are not registered with the server, so that's why we got the name hit registration issue. And so let's talk about another sort of problem when we take things online is input blocking. So imagine you're playing a game and you want to perform two actions sequentially, immediately, one after another. So the approach one, which is blocking the input. So basically you make the input for action one, you wait for that action to end, and then you input the input for action two, and then action two will be performed. So this way is not a very intuitive experience because the game have to wait for action one to end before receiving the input for action two. And any input while action one is being performed are completely disregarded. The game will act like it doesn't exist. So this might be acceptable for a single player game because like you want to run and then jump, you may have to wait for the run to end. This is not a great experience, but it might be acceptable. But if we take this approach online, it will introduce like a tremendous amount of lag. So let's look at a better approach to solve this problem, which is input queuing. So basically, say you want to perform action one and action two sequentially, one after another, you can actually press input one and then immediately press input two, and the game will read both of those input, and it doesn't matter if action one has ended or not, it will execute action two right after that. So this is why it got its name input queuing, because every input that you performed is put into a queue, and the game will execute those input sequentially. And this is even better because we can say map one action to a combination of input, right? So what if you what if you press input one and input two right after another, and we can map that to another action three. So this is a very, very good way to minimize the latency that when we play an online game introduce. And if this sounds familiar, it's actually how online fighting games work. So for example, in this game, usually if you have to wait for the action to end and then perform the input, that would be quite frustrating. But you can just press the input one after another and watch your character play out a very, very satisfying combo. So far when we talk about the keyboard, we have been talking about our North America and European popular QWERTY keyboard. But when we take things online, we also have to keep in mind that not everyone we play with or against are using this keyboard standards. So there are a few sort of um, international input standards that are quite different from what we are familiar with. So these are some of the sort of languages, and we'll see in a second their keyboard standard. And we also have like some Latin script languages and the keyboard input standards for these languages as well. So these are some of the international input keyboard of a few countries. So this is Russia, South Korea. You can see is quite different from what we are familiar with. Thailand. This is amazing, by the way. It looks so cool. Turkey. We see that we have some of the characters that we are familiar with, but they're not in the position that we expect. And we also have something, an example. So this is an example of the difference of keyboard input standards. So the Dvorak keyboard standard was designed by Dr. August Dvorak, and it is a different standard from what we are familiar with, which is a QWERTY keyboard. So as you can see on this picture, if we take the WASD standard that we are familiar with and apply it onto this keyboard, it would not work at all because all of the buttons are not in the position that we want them to. So we have to change that to a different standard. So in practice, so to conclude this section, is that if we hard code the actual keys that we want to get from our player, that might be problematic when we distribute our games internationally, or even just player who are not using the QWERTY keyboard standard. So in practice is so we've looked at sort of the basic theory of how input works in video game, the history of them, but how do we actually implement an input system in Unity? So input management in Unity. Now Unity have made their input system sort of very how do I say this? Very complicated to decide. So basically, Unity Input Manager, which is the legacy input manager that was introduced along with Unity, and recently they introduced a new Unity input system, which is the modern way of how to handle input in Unity. But they have not deprecated the legacy Unity Input Manager. So that's, I think, is still the most common way that Unity developers check for input is with this Unity input, the legacy input manager, which I do not recommend. I recommend the new input system because, in my opinion, it's very, very scalable for large projects. It makes it a lot easier. So to handle multiple input devices, as we have just talked about, and we can very easily tweak some of the input properties like sensitivity, dead zone, etc. So let's first take a look at the input manager, the legacy input manager, because it is actually quite good in some scenario because first of all it comes with Unity by default, so we don't need any extra setup. It's just there, and to query for input is as easy as you see here, an if statement, and we have ourselves some input managing. But this approach is might lead to some repeated code. You will have to query if statements for input, and this contradicts the try rule in programming, which is short for don't repeat yourself. And it is harder to handle input from multiple devices. Say you want to ship a game for PC and console and other devices, so you're gonna have to do all of that manually. And as you can probably tell, this is not exactly scalable for larger projects. So I would recommend using this legacy system for prototyping, because you don't have to do any extra setup or upfront work. It just worked right out of the box. But if you want to use it for a larger, more long-term project, I recommend the modern input systems. Or some of the advantages of this system is it's very easy to change input mid-development. What I mean by that is, say you have an input that is mapped to the spacebar button on the keyboard. But what if halfway through development you want to change that into a different button, say the E button? So you have to go into the code, find that if statement, and change it. So that's not exactly fast or intuitive. And as you can see on the image here, the input is tied to an action, not a key. So this is very important and very great, because now I can just go into the jump and change this, say, from space to E. And I don't have to go into the code, because the code is checking for the jump action, not the space key. And the example that I just gave was a perfect example of how it can prevent the some repeated code. Again, the dry rule in programming: don't repeat yourself. So that's why I really like, and it's also very easy to sort of add another input device. Say you want to add a controller, well, you can just add one more key under here and then map it onto, say, the A button on your Xbox or PlayStation controller. It's very easy. And so that's why I really like this new modern system. But it might not be perfect for everything. Say you're prototyping something, you want something fast and works right out of the box. So it might not be the perfect solution for that, because it is more work required, because you have to go into the package manager and download the input system package, and then it works. So, and the code for managing input this way, as you can see here, can be a little bit confusing for new programmers, because this is actually a lambda function, and you can break this into a dedicated function as well. So that's why new programmers usually do not gravitate towards this system, because an if statement is so much more understandable. And we have linked here a few of videos, only 2 videos, but on a way to learn more about this topic, I will link them in the chat so that we can click on them and access them easily. But yeah, these are two videos that are really interesting if you want to learn more about this topic. And that is the end of the slides of my presentation. So thank you so much for tuning in. So hopefully you have learned quite a bit about input management, not just in video games, but also in how to create one in Unity. So thank you so much for tuning in.